Thank you, and thanks a lot for coming. As I said, my talk is about basically how Haskell is a really nice host for domain-specific languages. And it's kind of, it really connects in some sense to Phil's keynote this morning, even though the topic is very different. Because one of the things I want to point out, how we are using the language features, the language extensions of Haskell, which in Phil's words, basically Haskell has because it wants to grow up and be like Agda, and how we are using that to embed a domain-specific language. So, I mean, with domain-specific language, you could kind of ask why do we need domain-specific languages at all? Because we have general-purpose languages, which in theory can do everything a domain-specific language can. And if you look at something like a small example, that's MATLAB, just a small expression which does some matrix calculations. So it takes matrices A and R and multiplies them with their transpose. So, and then with an identity matrix multiplied by a value, and then with their the left inverse of A. And we could write a library and express all of that. But the nice thing about a domain-specific language is that we are able to kind of provide the constructs and the notation that is familiar to the user of that and the expert of that domain. And then on the other side, we can also implement optimizations because we know more about the domain, and can kind of optimize more aggressively. That's not necessarily always the case. So in MATLAB's case, basically, quite often they just kind of call directly to highly optimized library functions. So it's in a way just a nice domain-specific interface to some libraries. So sometimes it really kind of there's a good reason to be a specialist and kind of focus on one particular thing. And there are basically countless areas where that can come in handy. But designing a new language, or kind of new languages, are really a lot of work. And they are not just a lot of work for the person who has to implement the language and design the language and implement the whole, basically, language infrastructure, but they're also a lot of work for the user who has to learn the new language. So a kind of nice compromise is embedded languages. What is an embedded language? It's basically kind of a language inside of a language, and it's a kind of a fancy name for a library which looks and feels like its own language. And if you read that statement, I mean, it's it's not a very clear criterion, right? It looks and feels, that's obviously very, very subjective. So the boundary between what's just a library and where you would say, well, that's already kind of an embedded language, there is no really kind of clear boundary. The advantages of that is that depending on how we embed it exactly, we can use at least the host language front end and tools. And it has a lower adoption threshold because we're using infrastructure of an existing language, and we're using the syntax of an existing general purpose, or the part of the syntax of the general purpose language. And that's at least true for users who are already familiar with the host language. But even for people who want to use the embedded domain-specific language and are not familiar with the host language, it kind of pays off to learn that because this language is also useful in other contexts. So the question is, what actually makes a good host language? And I think one important thing is basically that you have a seamless embedding, that we have these abstractions, but they don't kind of leak to the outside. So not kind of implementation details and complications of the host language should not leak to the outside. And because I kind of also care about software correctness, I also think it should be a safe embedding, in the sense that it doesn't make it too easy for the user of the embedded language to write incorrect programs which cause runtime errors. Support abstraction, and of course it should kind of support the domain-specific optimizations, which I mentioned above, because I think both of these things are basically the important, the point of a domain-specific language to begin with. And there are really kind of two main different types of embedding of domain-specific languages. And one are basically kind of shallow embeddings. What does that mean? Well, basically, if it's embedded so that the semantics of the embedded language is determined through the semantics of the host language. And basically, really, that's fairly close to just a regular library. So for example, if you go back to the MATLAB example, and we would just kind of try in our host language to mimic the syntax, maybe overload these operators so that they kind of call matrix multiplications, which are then basically intelligent enough to figure out the kind of flexible inputs. And but essentially, like we can overload these things and we can choose a good representation for the data structures we're working on. But we are kind of, the semantics of a function call is still the semantics of a function call. And we rely for that on the host language, and same for the memory management and everything else. So we don't have that in our control. And in particular, it's kind of difficult if I want to not just implement my matrix multiplication very efficiently and my matrix addition, but let's say if I want to make optimizations which go across those operation boundaries, I can do that to some extent by being very clever in the way I represent the matrix, but I have to kind of play according to the rules of my host language compiler so that it works together well. So it's really limited, but it's also very lightweight. But what's kind of more interesting and more powerful are deep embeddings. So what is a deep embedding? It basically means that the language operations kind of don't just directly call or directly indirectly call some other host language functions, but they do build an intermediate representation of the domain-specific program. So going back to the example, calling this would, for example, build an abstract syntax tree. And it's not important here what it exactly looked like, but it's basically, it's kind of just a data structure that represents somehow the program we built, but it doesn't have any intrinsic meaning. So I can take this tree and then, for example, write an interpreter in the host language that executes whatever this program represents, or I can write a full compiler in the host language that compiles this to some specialized hardware or some FPGA. So I can basically do anything, and for the same language, I could provide different backends. So it's completely under my control, but it's also kind of my responsibility, and it's therefore also more work. So I want to basically explain some of the things we're using Haskell for, using an example language we're working on, and this language is called Accelerate. It's deeply embedded in Haskell, and the domain it targets is kind of high-performance data power computations, regular computations, so they can be nested. We have arbitrarily kind of multi-dimensional matrices and things and operations on them, and we map them to hardware. So the idea basically is that For some applications, you really still, despite all the progress in compilers and the hardware and everything, you really still don't have enough computing powers, so simulations are very good examples of that. And to execute that, you want to exploit some specialized hardware. But the problem is this hardware is very hard to program. So we all have GPUs, and how many people have kind of tried to write programs for the GPU? And it's generally a fairly painful experience, right, to get kind of good performance out of it. And it's kind of a painful experience for people like us who really like programming and who, programming is kind of our job. But the scientists who want to express this, that's not their job. And they spend a huge amount of time, basically, and their PhD students spend a lot of time doing that. So the purpose of Accelerate is basically trying to take some work from them, make it easier for them, and still have performance that is at least as good or better as hand-optimized code for these architectures. So I said it's a deeply embedded language, so the way it works, I write my Haskell program with Accelerate, and then I compile it with GHC. And then I get the binary and I run the program, and during runtime of that compiled, but GHC compiled program, it will generate my parallel program, my Accelerate program, and generate target code at Okay, so 2 minutes or?
May I have your attention?
2 minutes break.
May I have your attention, please? The public address and fire alarm systems are about to be tested. The fire alert signal will first sound, followed by the fire evacuation signal. Please take no further action. The test is now complete. If you have difficulty in clearly hearing messages or fire alarm signals, please advise main reception. Thank you for your cooperation.
So at least all of you should be awake again now. And it took a lot less than 2 minutes. So basically at runtime, it generates that code, sends it either like we have 2 main backends, multi-core CPU or GPU backend, and then copies the result back. And this can kind of happen arbitrarily many times. So the system tries to be intelligent about reusing code and caching of that. So, but this can happen a lot of time. But the problem here really is that any kind of error in the Accelerate program, if the user can construct an incorrect Accelerate program, which, unbound variables, type errors, they become runtime errors. And so we really have to be, in this language, fairly good at making it hard for the user to write incorrect programs we can't actually map to the target architecture. And so I said the talk is basically about Haskell, and I will mainly talk about Haskell GHC specific extensions and how we're using that. But generally, there are lots of properties of functional languages, of which functional languages often have. Not everyone, and every language is lazy, but most of them offer some laziness, which kind of make them good host languages in general. And one probably fairly, not very spectacular feature, algebraic data types. Is this really something that is fairly central to it? Because, well, we all kind of know how to write, a simple AST data type, and you can write it like this, and it has just integer Boolean values, addition, and so on. And then we can wrap it, because we don't want to expose the constructors, we can wrap it into some more or less nice syntax. And now I kind of already have implemented my very, very simple domain-specific language, embedded language, and I can write things like that, and it will build an abstract syntax tree of that expression. But the problem with this representation is, as I guess most people know, I'm working in a strongly typed language, but my embedded language here has no types at all. So if I write this integer 5 and true, the Haskell type checker is happy with it because both are expressions and end needs two expressions, but it doesn't make sense in my embedded language. And here I had to to lift the number into the language. I have this kind of constructor, which is also not that nice. But the solution for that, and kind of one of the scenarios, really one of the strong motivations to include generalized algebraic data types, is that we can express types like that. So we can write the data type definition like this, and there we can see where we explicitly list the arguments in the result type. And in general, in regular algebraic data types, we have to have a kind of different argument types, but the result type has to be exactly the same. And with generalized algebraic data types, so I can parameterize a type also in regular algebraic data types, but with generalized algebraic data types, the type constructor is obviously still the same, otherwise they would not be expression data constructors, but it's not exactly the same because it has a different parameterized type. And this is nice because now I can express the fact that end needs a Boolean expression, two Boolean expressions, and then I get an error here if I try to write that. And not only if I write this as a term, basically this definition also makes it impossible for me in Haskell to write a program that returns an IL type, that generates an expression. It's not just that I can't basically write them down literally. So this is really important if I want to exclude the possibility for these type errors to happen. Now, let's kind of go back to accelerate and how that relates and what kind of things we're doing here. So I said with domain-specific languages, in some sense, the integration should be fairly seamless. So it should be easy to write such a program. And with accelerate, we kept basically the Haskell style of defining operations. So, for example, if I want to write my dot product in Haskell, I have two lists, I zip them, and then I calculate the sum over the zipped pairs. And if I don't add any information, I will basically use the prelude list implementation of that. And the problem with this, of course, is if I care about performance, is that lists have all the elements are boxed, and even though there's some optimizations happening to avoid intermediate data structures by GHC, it's not really kind of that performant. So I can just replace the data structure, and if I want something more C-array-like, I can import the vector library and use basically unbox types. And kind of if you're generous, we could already basically say the vector thing is something like a small embedded, shallowly embedded language. And the vector library does do a lot of optimizations, basically by having a very clever representation of vectors, which ensures that I don't really have extra data structures. And so it has basically a lot of intelligence in the representation. But if I now want to actually be if that's not enough, and I want to execute in parallel, I have to change my program slightly, so I have to drop the L of the fold. And why is that? Well, a fold left or fold right is inherently sequential, right? It adds it up, like if you have the accumulator from one of the other sides. So I can't have that in parallel. So what I have instead in accelerate is a tree fold, which I can run in parallel. And apart from that, I just have to import another library. And now, again, the types are what was unboxed is now ELT type, which just means that it has to be a legal element type we support in accelerate, and that's kind of limited because we can't map every type efficiently to the GPU. And the other interesting thing is, or the other really different thing, is that the result values are wrapped into this ACK thing, and that is basically exactly like the expression type. So it says that this operation takes a computation, a parallel computation that produces a vector, another one, and it gives me a new computation. So it does not return the values, but it's deeply embedded. So let's have a closer look at the actual type of fold. So there we have this accelerate, basically the ACK language, and this which expresses collective parallel operations. And the first argument of fold is yet another kind of embedded language. This is a language of sequential operations. So it says fold takes a binary sequential operation and maps and reduces an array with that. Why do we need to distinguish these two like sequential and parallel operations? Because we can't express, or we can't compile arbitrary nested things, because otherwise, if that could be parallel, it could be very complicated, and we can't compile that. So the type here makes sure that I don't kind of sneak in irregular computations, and that's kind of stopped. The other thing is that I pass something like the shape type. So if you look at this, this basically says that I take an array of shape, something with an integer, and I reduce it by one dimension. So it can take an n+1 dimensional array and return the n-dimensional array. And the shape type is basically just the SNOC type list. And then dimension 0 are just kind of abbreviations. So scalar is actually a 0-dimensional array, vector a 1-dimensional array, and these shapes are in the class. So the real type of dot product in this language is actually it takes two arbitrarily the matrices of arbitrarily dimensions, but the same dimensions, and adds them and reduces them. What it does not track, so it tracks the dimensionality, but it does not track that they have exactly the same shape. That could be with something like the natural numbers Phil talked about this morning. We can also project that into the type level in Haskell. So if we wanted to, we could track that. But for accelerate, we think it does not make much sense. The next thing is here. The second argument is basically the neutral value, or the starting value, and it has type expression A, but in my example, I wrote just plus here, 0 here. So in the initial example, I had to have this lifting into the target language, the embedded language, which I don't seem to have here. So how does it work? Well, we basically just use overloading here to lift some of the values into the embedded language. So 0 actually is already not just a value, it is an overloaded value, which really is a kind of function. So what we do here, we use type constraint synonyms. So we have a synonym for the num type, and we say, well, this is anything which is a synonym for something that's in element type and an expression. So now 0 is overloaded, and with it, kind of the functions on numbers to work there. So that works quite well, and it's not a lot of work. Unfortunately, it does not work all the time, that it kind of just gets automatically lifted and the user is not exposed to it at all. Because not all values are overloaded and not all types are overloaded. So for Boolean values, for example, even though it's possible and there are libraries which overload bool, it's not what we usually expect. So we can't overload that. So we need some kind of lift function that explicitly takes this, takes a Boolean value into the language, but it should also do things. For example, if I have two expressions of type expression bool, and I put them in a pair, I want to lift that into an expression of pairs. So what we use here in this time, to keep lift flexible enough, we use associated type synonyms. So we declare the class of liftable types, which are kind of a relation between the constructor and the element type. And this associated type synonym, associated type, basically is just a function that is local to the class definition, which tells me how to map a given type into its plain representation. So plain just strips all the expressions and then lifts it into basically an expression of plain type. So we use the associated data types to do that. And that is really flexible, but it also really has some annoying side effects. So for example, it should also be possible, so if I have an integer, like if I don't want x to be overloaded and I wanted it to be an expression in, not an expression of num a, then I think should be okay to just say x is expression int, and I lift 9 explicitly. But because it can't now do proper type inference and type checking anymore with my associated type synonyms, I get this really kind of annoying type error message. And for people who kind of know about associated type synonyms and all these things, that might be fine, but it's supposed to be an embedded language, and we want to protect the user. And the plain type is something that's actually internal to the implementation, so it really should not be visible. So that's kind of annoying. And we have a similar problem, basically dual problem, if you want to take something out of the language. So if we have an expression a and we want to take a out. So in general, that's the only way to do that, because expression A in an embedded language is a program, is kind of to run this program. So generally, I need some kind of evaluator or something to run the program, and then I can get the A. But there are times when we can actually, for some values, we can get the A without executing the program. And that is when the type already kind of tells me what the value has to be. So obviously, if I have an expression of unit type, then I really don't have to compile the program and run it. I know that it's a union type. So I can extract that. Now, that's not the case often, but I can do a similar thing. Basically, as long as I know that the top-level constructor is unique, is clear. So if I have something of expression AB, I know the result will be a pair. So I can extract that. So I can define a class unlift, which is basically a subclass and goes in the other direction for some types, not for all of them. And where do I need that? For example, if I want to write my swap function, assuming it wasn't already implemented, then what I do, I kind of unlift the expression v. So then it becomes a pair of expressions. I can extract the two expressions, put them back together again, and lift them again. Unfortunately, here I get the same kind of error messages, and I have to add type annotations. And that's really, again, something that is not really obvious to the user. And also it's kind of annoying because if I want to use view patterns, so instead of unlift, AB, and pattern match, pass it to unlift and then do this view pattern matching, I can't type annotate that, so I can't use it. So it's basically kind of hard to understand the error messages if you don't know the internals, and it's also annoying to use. And also, I said I would like to have a seamless embedding where the internal things don't bubble up. It's not really the case because we expose all this. So the good news is that if you look at the patterns where these unlift things are used, it's basically used because I want to access Haskell's pattern matching. Right? I wanted to pattern match on the pairs to take them apart. And for that, we can actually fix the problem in a really nice and convenient and safe way, at least for product types and any kind of product types. So we use another extension of Haskell there. Who of you, are you familiar with pattern synonyms? So basically what it allows me to do, let's say I have a fairly complicated data type and I want to either hide that and want to have a nicer pattern, maybe which just kind of looks at parts of it, or I have an abstract data type, which I don't want to export, but I still want to allow pattern matching or a controlled pattern matching on it. Then what I can do with this pattern, you would basically define my shiny new convenient pattern, and then the work is done in the complicated pattern, and I can use that shiny new pattern both as constructor and destructor. So I can do that, for example, in what Accelerate does. It provides these for all tuples of, unfortunately, we can't reuse the pair thing, so we can't reuse the name, but what it does, it kind of gives you pattern synonyms for pair things, and then I can match here, I can use T2, which is a pattern synonym, to take the expression apart, and on the right-hand side, that always takes me longer than it should. On the right-hand side, I can use it as a constructor. In Accelerate, it's also possible for users to define their own data types, and we have mechanisms that they can kind of easily provide these view patterns. So it's also possible for user-defined data types to some extent. So this problem of deeply embedded languages that we kind of are in the expression language, we want to do pattern matching in these things. So we would like to have basically a hybrid of shallow embedding and deep embedding is a very common language, basically. Most people run into that. And there are other approaches. For example, in Feldspar, they have kind of a different approach to solve a similar or the same problem, and it has kind of different slightly different properties, but if you're interested in this problem, then it's kind of nice to read that paper as well. So that was one thing we used, and then the next thing we need to think about is basically there are also kind of two different types of deep embedding, first order and higher order embedding. And basically the difference is kind of how do we deal with variables, lambda abstractions, and bindings in these two. So first order basically says, well, variables and all of this, they are just kind of regular language constructs, and we treat them like everyone else. So if I want to add variables to my language, I try to just add them and say, well, a variable is a string or some kind of identifier. You probably wouldn't actually choose a string, and it basically represents an expression. But with a variable, if I just look at the variable, I don't know what type it is. So it's already a bit problematic in this type language because it says it has expression A, and then lets and lambda. So no one here is aware that, none of the constructors are aware that variables are actually really kind of special beasts and should be treated differently. And it is actually kind of, from the type level, it's not really correct there. So, but basically, such a first order embedding has the problem that I can't now statically ensure that things have basically the right type. So higher order embedding use the host language and the host variable bindings. And that is what I did kind of for fold without even kind of mentioning it. Because if you look at the type of the fold of the reduction function, it's a Haskell function type, not a type. So it's not an expression which represents a function, but it's a function that combines expressions. Same with map. So the nice thing about it is I can just write regular Haskell lambda expressions and feed them to fold and map in accelerate. However, at some point, so we can express that, but now if I want to generate code for it, and I have these Haskell functions, how can I, they are not really expression trees, they are just Haskell functions. So somehow I have to convert these lambda expressions into something tangible where I can generate code from. So I have to convert it back, so convert the expression functions expression AB to expressions AB. And what I can do, for example, it's a simplified example, but let's say I have an AST node that has such a function of type expression AB. Now, and the function might look something like this, so a Haskell lambda expression, but I can't inspect it. But what I do now, if I basically hide the constructors, I know that inside a constructor can't actually be inspected. So if this is a regular function, and if I apply this function to an identifier, which I haven't, a first order identifier basically, which I haven't exposed to the user, then what I get back is basically an expression that has this identifier expression where the variable was. So I can fairly easily get from higher order to first order. And then I can read it. So now we can basically make sure that the user program is type correct and the variables are in scope by using higher order. However, then we convert it back to first order, and there I might make mistakes. So the internal representation, if I get something wrong, or if any of my optimizations destroy the correctness, then that is not checked statically. So this can then cause bugs in my compiler, can now cause runtime errors in the accelerate program. And we can kind of increase the type safety there. And again, this connects to something Phil mentioned this morning. He mentioned the Brown notation, where we can kind of represent identifiers instead of with names, which is nice for people, but not that nice for machineries, with indices. So the idea is you basically get rid of the names and instead have an index that tells you where the variable was bound. So here, the index 0 points to the closest lambda, in index 1 to the one, basically one out. And similarly here, so now it's kind of just an index. So it's very hard to read because here we have the same index, the same variable x, but here it is represented by two indices, by two different indices, because here it points to, like it's I0, because that's the closest lambda, but here it's kind of pushed one level deeper, so the same x is now I1. But the nice thing is that we can use that to encode basically in the type the nesting level of a variable. So we can have typed environments which know which values they have at which position. So we use GADTs for that. And then, for example, an environment that is a stack, and it has true and 5 in it, and the type basically says that on the bottom of the stack is an integer, and then it's a Boolean value. So I can see in the environment what the type is, and then I can encode identifiers in a typed way, so the identifier knows what type of environment it needs to basically be legal. So 0 index, so I0, can kind of deal with any environment, and it has type T if on the top of the environment a value of type T. There's a value of type T, and the successor, so it's kind of just a more complicated variant of the natural numbers, knows that it's in the stack. And then I can use that now in my expression and say a variable is constructed, takes an identifier which needs an environment and gives an expression of that environment. It basically, with this environment, will evaluate to value t of type t. Constants, for example, they are fine with any environment because in a constant there's no free variable. And here I kind of bind with the lambda expression, then it binds the variable. So it needs an environment with one less. A lambda has one less free variables, so it kind of pops the environment from the stack and puts it here in the result type. So this way, I can write a total evaluator function when I say, well, an expression of this environment, which needs an environment env, can evaluate to t if I give it an environment of exactly that type, and then it's a total function, it will always evaluate. There's no variable out of scope and no kind of variable misused. So I now have an internal representation that is also typed. Then with let expressions, which we also use from the Haskell let expressions. So here in this example, I had VS, which was used twice here. So conceptually, basically, this will build an abstract syntax tree where VS occurs twice. But now if I use that syntax tree to actually generate code, then I would generate code for this syntax tree twice. So that's not good. And I also know that internally at runtime, it's not this data structure that is produced, but Haskell has sharing. So there will be pointers to the same data structure, which I can't really observe if I don't do any dirty tricks. So we have to kind of use some dirty tricks and use something called stable names, which gives me basically checks for referential equality, which Haskell usually does not have. So for a given object, it gives me back a stable name, and I know if two names are the same, then it actually points to the same object. The other way is not guaranteed, but basically it's good enough so that I can recover the sharing. And this is an I/O effect because, well, it is a side effect. This representation is not something that is kind of supposed to be there from a declarative point of view. So once I have that and I combine, so I have to combine both the De Bruijn transformation and the sharing recovery. I have to do that at the same time, because if I would do the conversion of the indices first, then my tree, like I would lose the sharing. So it's a bit kind of tricky to get that right, but then we kind of get a nice first order abstract syntax tree where we still have recovered the sharing that was present in the tree. And again, this is a problem all embedded languages in Haskell have, which have this higher order embedding. And for example, Andy Gill encountered that in his hardware specification language, Kansas, Kansas Lava. And in his paper, again, he describes this as well. And in the Accelerate paper, there's a different description. So we use higher order embedding for user convenience and safety, and first order generation. So the question, kind of, I showed you how we can carry this type information around in the tree, and in Accelerate we maintain it until we really generate the LLVM code. And the question is it really worth it? Because you have to go through quite some effort to do that. And I think for user level checking, it definitely is. For the type compilation, in our context, it is, but it really depends on your language. So just because you can encode everything in the type system might not be worth it, because it makes transformations a lot harder to do. So that kind of can be done, but look at it more closely. So overall, kind of the conclusion for me is Haskell and HC extensions provide really a great way to embed DSLs. There are, like, it's not perfect, and there are lots of spots where the abstraction is really leaky. But in my view, kind of, if I had to point to the main pain point when I try to get people to use a language like Accelerate is not on the language level, but is on the tooling. So the scientists we're working with who are using it, they can deal with horrible error messages. I mean, they usually work with horrible languages. But what they like to have is something like Jupyter Books. So integrations, I think, work to have these things for Haskell, which is happening. I think is actually really, really more important to get an adoption for people who are not using Haskell already than necessarily kind of fancy type abstraction of types and stuff, which I really love. But yeah, I think the IDE thing, the tooling thing is the main point. I think, sorry, it's kind of a bit longer.
Gabriele, thank you very much. Unfortunately, no time for questions, so I'm sure we'll be able to grab you in the lobby or whatever. But once again, big round of applause, please.